an honor and privilege to read the biodata of Mr. Himadri Sekhar Bhattacharya. Mr. Himadri Sekhar Bhattacharya received the BTech from Techno India College of Technology in Electrical Engineering and MTech from Kalyani Government Engineering College in Electrical Engineering with the specialization of Power System in 2014 and 2017 respectively. He was a full-time research scholar of IIEST Shibpur from 2017 to 2022. In this tenure, he has published multiple journals and conference papers. After submission of PhD thesis, he has joined one of the reputed EV company of India. His major working area revolves around force-based vehicle modeling, cell and pack-based electrical modeling of lithium-ion battery, parameter extractions with different optimization techniques, Kalman filter and deep neural network based SOC estimation, machine learning based SOH and EOL estimation and performance analysis. He also received the best paper award in electric vehicle section in 8th International Conference on Power Systems in 2019 organized by the Electrical Engineering Department of MNIT Jaipur. Once again, I welcome you, sir, for the talk. Over to you, sir. Thank you.
Thanks a lot for a nice introduction. So may I start my presentation?
Yes, sir.
Okay. Is it
Your slides are visible, sir.
okay? Thank you.
Thank you very much, sir.
I hope everyone can view this.
Yes, it is visible from our end. Yes, you please carry on. Yes.
Thank you. Okay, thank you. Very good afternoon to all of you. So, I would like to thank Professor Orno Ghosh from NIT Rourkela for inviting me, and it is a really great honor for me to be a speaker in this great platform. So, this online STC on power electronics converters application in microgrid and vehicular technology. My lecture will be on modeling and on-load parameter estimation of lithium-ion battery electric vehicle applications. This is the entire outline of my work. So here we can see the introduction, that is based on the global EV sales from 2020 to 2030, what will be happening in this current decade, and
sorry to interrupt. Sir, please click on the hide option, sir. Sorry to interrupt you. We are able to see that one instruction. Please click on hide, sir.
Okay. Sorry.
Thank you, sir.
So in the last few years, we our country. So the major pollution is based on the transportation section. So our future approach will be to minimize this thing and make the India as a zero carbon transportation system. So our government has already taken multiple initiatives on that, and we as a researchers should also uh, take a great advantage of this and should try to make ourselves directed in this particular direction. To there are multiple fields in EV section. The most used one is obviously the battery, because it is the heart of the vehicle, and in a four-wheeler it took almost 60% cost of the vehicle. So how this cost is getting optimized over time, that part is obviously from the different materials that we'll be using in future, because people are already working different in sodium, lithium sulfur or sodium ion. Different kind of technologies are already there, but still lithium ion is the best one in terms of application point of view. So with the growth of this EV section, the research will also increase obviously. And as we can see in global battery demand also, it has highly increased, and it will increase like in 2025, it may be 1000 gigawatt hour, but as the global, as the entire world will in like improve, and this to up to 2030, this part will be around to 2500, so more than 2 times, 2.5 times it will increase. And obviously we can see that the demand is the one of the most important thing, that as we know, lithium ion battery can be used apart from electric vehicle, different energy storage section, as well as some consumer electronics, but the major part will be taken by that, around 90% will be for electric mobility purpose. And we can see here that how the countries, the first world countries, are improving themselves to adapt this part. So we can see that maybe in 2030, obviously as of now, we know China has greatly improved in this particular section, and in 2030 it may took around more than 40% of the global demands of EV. So now coming to the basic components of the lithium ion battery. As we know, in all the batteries, there are one positive electrode. Positive electrode is known as the cathode, whereas negative electrode is known as the anode. So during discharge, it gives the electrons to the external circuit and is oxidized. And in case of charging, it accepts electron from the external circuit. So it is for like anode, and for cathode obviously the reverse thing happens. During discharging it accepts electron, and during charging it gives up the electron to the external circuit. And what are the other components? Other components are like electrolyte. As electrons moves in the external circuit, compensating ions must move internal to the cell. So here in the figure 3, we can see that how the electron is flowing inside the cell and outside the external circuit through the load or the charger, depending upon the application, whether the cell is charging or discharging. So there are other functions of electrolyte also, like cations and anions with net positive charge. During discharge, they move through the electrolyte towards the positive electron, and obviously the anions will do the reverse one. And electrolyte produces the medium for internal ion charge transfer between the electrodes. And the electrolyte is typically a solvent containing dissolved chemicals like acid, base, salt, providing ionic conductivity. It must be an electronic insulator to avoid the self-discharge. And another part is separator. The separator is actually separating the positive and negative electrode to avoid the short circuit and self-discharge of the cell, and often made of glass, mat or fiber or polythene or a polymer. Current collector, since electrodes are often made from powders, current collectors are metal foils to which electrodes are adhered that conduct electric current to cell terminals. Now the comparison of different lithium ion chemistry. The first one, the first advantage and disadvantage of different lithium, this lithium ion battery is discussed, and the figure can represent the different properties of the cell depending upon their chemistry. So the advantage we all know, that is, it is high energy density, higher voltage, typically about 3.7 for lithium ion, versus 1.2 for nickel millihydride or nickel cadmium. A single cell can be used, and the lower self-discharge rate, that is its cycling, that is calendar aging, is very minimal, and also a longer lifespan. The lifespan, depending upon different chemistry, from 600 to up to 2500 to 3000 cycle, it can. We all know that one is major more expensive, that is lithium is a really a costly metal, we all know. So, and it is not also available throughout the world, so it is a very costly in terms of developing a cell, and also more manufacturing complexity. It is not as as simple for lead acid batteries, and need more reactive chemicals. It is obviously less stable and requires special safety precautions, because lithium is highly dependent on temperature. In last few months, actually, we have seen different reputed companies EV scooter has been burnt due to this temperature issue. So for that, the special safety precautions are needed, and also special circuitry for protection. That is the special circuitry for protection. These two things means it is actually indicating the operation of BMS. Now we will come to the BMS. What is BMS and how it will work? And let's continue further. So impurities limit cell performance. So obviously the amount of impurity present in different chemistry, the performance varies. Now performance depending upon chemistries and manufacturers as well. So same cell can be made by different manufacturers, and their performance is highly varied. And similar for a same manufacturer also, if a same manufacturer is making different cells depending upon different chemistry, so their performance obviously varies a lot. Now the functioning of the battery management system. How the battery management system? It is nothing but an embedded system on a PCB. So it is entirely a power electronics thing. And in figure 5, we can see how it is actually operating in a battery pack. So in a battery pack, what is there is number of cylindrical or like different types of cell are there: pouch cell, prismatic cell, coin cell. But obviously coin cell no one is using in this particular application. It is mostly limited to cylindrical, pouch and prismatic. So here we have represented the cylindrical cell, that is the mostly used one. And in terms of cylindrical cell, we can see there are different types also. One is a 18650 and one is 21700. And recently Tesla has made a top less cylindrical cell of 4860. So there are different specification depending upon its height and weight, and obviously their performance. So this is how the battery pack is made, with series and parallel connection. And it is the way the BMS is actually embedded. Here we can see there is only one BMS, but there are multiple packs in the world is currently using both two BMS part. So in two BMS, one is working as master and one is working as slave kind of a thing. So it is the certain outline of BMS. And now coming to the fundamental features of BMS, what a BMS exactly does. The BMS is actually a combination of hardware as well as a software. So like hardware part, it actually sensor system. The sensor system, we can see that from a BMS what we can get only the voltage, current and temperature. These are the only sensor based signals the BMS can give to the manufacturer. No, sorry, that means the user, or like us, the researchers. So whatever we have to do, we have to use only these three parameters, nothing more. Now coming to the protection circuit. The protection circuit is actually protecting the cell from different perspective. One is thermal management, it should not go beyond a certain limit. So protecting a cell and making it safe and secure for operation. For a reliable operation, else it is highly inflammable. So we all know what hazardous situation can happen. Now coming to the charge and discharge control, like overcharging a cell is not a good option for its life, as well as discharging a cell to a certain value is neither the same one. So we have to operate in a certain limit. Every cell in their manufacturing spreadsheet is given what should be the operating range or what should be the charging voltage and discharging voltage. We should not go beyond them. So one of the major part of this hardware system is to control this charge and discharge of the cell. Another part is thermal management. In a pack, the cells are placed in different parts. So based on that, this depending upon their position, whether there might be cooling or not, that is a separate issue. But there are actually temperature variation depending upon their position. So the temperature of one cell could be increased greatly, but not others. So that cell may function differently, or that can make that entire pack inflammable one. That if this thermal management is not there, so this thermal management is highly important. And another part is communication. The communication is basically nothing but a CAN bus, which is actually getting the data and putting it to the cloud. So whatever BMS is doing, not only storing the data in itself, it can directly communicate to the cloud. And obviously there are certain companies in our country, they are actually taking the data from the cloud and they actually use the algorithms or anything in the cloud so that it can directly operate to BMS also. So it is basically a two-way system from BMS to cloud and from cloud to BMS. So this communication or CAN bus is responsible for that. Now coming to the software part. The software, what does this cell or what does BMS does? That is, one is battery modeling. So there are different types of modeling. We can see in the literature that we will obviously come later of this presentation. And the other part is state estimation. State is, here I have given it SOC, SOH, which are currently using, but there are other state also, like state of energy, state of power, and different other estimation also that researchers need to focus on. So, and another thing is important thing is cell balancing. So in a cell we can assume that all the cells are identical, but it is actually not. So they are, and they might be from same manufacturers and same chemistry, but still every cell are not in lot identical. They have slight differences, and depending upon that, the voltage of one cell may drop or certainly rise. So based on that, we have to balance the cell. There are two different techniques for balancing. One is active balancing and one is passive balancing. So but active balancing is too much costlier. That is, in presently most of the EV manufacturers are working with this passive balancing. Now coming to the fault diagnosis. Fault diagnosis and health management. Like if there is a certain fault in the system, like there might be internal short circuit or different other faults can happen, or also the cell may degrade to a certain level so that it is uh, the health is not like reliable for further operation. So these things are actually taken care by the software part. And also the user interfacing, the one I said, like that how to contact with the um, manufacturer or this pack manufacturer. This is actually done by the user interfacing, how to integrate data from this uh, BMS through the software, that is taken care by the software set also. Now I have started this vehicle modeling. The vehicle modeling, why it is important? Because there are different force are getting applied at a certain time to the vehicle. So depending upon this vehicle, how the signals, when I'll be telling signals, that means the voltage, current, temperature. So the part is here, we have used a simulative vehicle models. So there are different forces we can see, that is the rolling resistance force of the wheels, and the aerodynamic force that is getting by the car itself, and the hill climbing force. It is very much important because of this angle sine phi. This phi is actually zero when it is running on the road, but while it is going upward or downward, this hill climbing force is actually contributing to the force based modeling. The linear acceleration, for linearly accelerating in a road, this linear acceleration force is needed, and another one is angular acceleration. So the total tractive force is actually the combination of all these five forces. Now we know that these equations, and based upon the equation, the torque is actually getting calculated. The torque is the equation 10 we can see, and in case of normal driving condition, the motor or the motor is actually running as a motor. But in case of regenerative braking means when a car is coming down in a hilly area, so without putting any force, the motor is actually behaving as a generator. It is actually feeding power to the battery, not even extracting any certain power from the battery. But in a normal driving condition, we know that battery is the only source of power. So this motor output is basically tractive force divided by the efficiency. And the motor input is actually motor output by the motor efficiency. Now in regenerative braking, these values are here, and the total battery power is actually the motor input, whatever input the motor should take, plus the associated or the accessory power. The accessory power means there are lights, fans, AC, or different other components of a vehicle. So that is also taken care by the battery. Now the specification of the proposed model. So these are some specifications like the mass of the vehicle, and the aerodynamic, the area, the other components, that the gear ratio or the gearing efficiency or the regenerative ratio. This rho is the air density, and n and m, these two are very important. N is the number of cells in series, and m is the number of series branches in parallel. So if we calculate the total number of cells of the pack we have developed here, it is actually 84 into 50. So this is the total number of force, and the accessory power we have taken it as a 250 watt, and the rated capacity of the pack is 120 H. But we know that the rated capacity is not the actual capacity. So we have tested our cells, and based on the combination, we can see from that figure 9.8 that the temperature is affecting the actual capacity. So it is not exactly 120, rather it is showing this kind of a characteristics. And another part is the internal resistance of the cell. We have tested our cell, and we can see that this internal resistance is the function of SOC, obviously at different SOC level from 0% to 100%, and it also varies greatly with temperature. So these are some of the values we have used in our model. And in case of this motor efficiency, this is the equation, and the other values are also here. So here we can see that the torque value is maximum 200 and the speed value is maximum 800. So between this torque speed relationship, that the lookup table kind of a thing, we can calculate the motor efficiency. Now another important parameter we have used here is SOC-OCV relationship. The SOC-OCV test is actually we have done in a lab setup to specify this SOC-OCV relationship because these two are highly related. So this is the testing protocol that we have presented here with a very slow current, that is 0.05 C. So I think the C rate is may not be familiar with all of you. So I will take a very short time to explain that as with. So the C rate is actually the amount of current by which the cell is testing. This capital C is nothing but the capacity of the cell. So if I mention that this 0.5 C, and if we assume that the capacity is 2 ampere hour, that means the current will be 0.05 into 2, so it will be 0.01, sorry 0.1. So this will be 0.01, sorry 0.1 ampere. So this current is required. And another thing is the fraction, that is the 0.05 C. This, if we reverse this fraction, so if we reverse this fraction, then it will be actually 20. So this 20 is the total amount of time. 20 hour is the total amount of time required to test the cell with a current of 0.1 ampere. If you multiply both of them, you will get 2 ampere hour. So we have tested our cell with this certain protocol. We have made a proper resting period because the ions are very much movable part. So to stabilize the ions, we have rested the cell for 2 hours and also discharged the cell as well. And we can see that there is a certain difference between charge and discharge. So the difference is known as the hysteresis. And here for our mathematical implementation, we have taken the average of this charge as discharge. And in the figure B, you can see that the average OCV at 3 different temperature is also represented. Here we can see that this SOC-OCV relationship is also dependent upon temperature. So we have used MATLAB curve fitting toolbox for fit this SOC-OCV relationship, and we were confident about this 9th order polynomial because this reduced R square value is coming as 1. So these are the coefficient you can see in table 2. Now these are the drive cycles we have used. These drive cycle patterns we have taken from NREL website that is open for access. In this drive cycle, this is nothing but a velocity versus time graph. This velocity time graph represents the if a vehicle is running in a certain driving pattern, what will be the current, voltage or temperature the battery will supply. So this is nothing but a driving profile. So here in our Simulink model, we have given the input at the drive cycle, which drive cycle we are incorporating, and based on that the velocity is getting calculated, and by the equations this distance, angular velocity, tractive force, and those will help us in calculating the tractive power and torque, the torque, speed and efficiency relationship we have seen. So from that we can calculate the motor power input, motor power output, efficiency of the motor, and the motor power input will also get calculated. And then coming to the battery power, the battery power will clubbing up with the accessory power, and that will give us the lithium total, the internal behavior of the cell, that is current, SOC and terminal voltage. Here that from the current the SOC is actually calculated, and it is with the help of Coulomb counting method. We will come later with this part. And here we have done this for 3 different temperatures we have already mentioned, that is 10, 15 and 25. Sorry, 10, 25 and 40, 15, 25 and 45. Now coming to the simulation result, here what we have done, here we have actually used separate slope angles. The one I was previously mentioned, that in a hilly area the slope angle may increase, and in a plane area this slope angle might be 0. So here how the slope angle is actually affecting the different uh, signals of a vehicle, so that we have represented here, and that too for 3 different temperature. And this is the simulation result for another driving cycle. Its name is NYCC, and it is for the BCDC. So throughout our work, we have used these 3 drive cycles. Here we can see that as the temperature increases, uh, as the slope angle increases, the amount of current or voltage is actually dropping very faster. At 0 degree at 0 degree slope angle, the what is the voltage curve, and with 5 degree angle, what is the voltage curve? We can straightly relate that if a vehicle is running in a hilly area, so the amount of this slope angle increases, the voltage drops very faster. And obviously same for the current also, and same for the SOC also. So how this slope angle is affecting the SOC. And here is we have calculated the range also, like what is the total amount of distance that the vehicle can cover. So here we can see that distance is actually covering higher for a 45 degree centigrade, and that is also dependent upon slope angle and temperature. So this is for the 3 different drive cycles. Now coming to the modeling part. So there are different lithium-ion battery modeling is there. One of the major one is electrochemical impedance spectroscopy modeling, though it is mostly in research now, but its real life application is still a scope for the researchers. So so for that we have used 4 different um, complicated, or we can see the models that can directly replicate the cells. Here we have used 2 different cells. One is BAK and another one is Samsung cell. So these cells were in spectroscopy, and then with the fitting of this spectroscopy curve, we have developed these 4 equations with the different optimization techniques, that is PSO, GWO and TLBO. I think we all are familiar with this kind of meta heuristic optimization algorithms. This is the specification. One is NMC and another one is LCO, and these two are almost the same. Only the nominal voltage of BAK is 2.4 H, but for Samsung it is a slightly higher, 2.6 H, and the rest part of the nominal voltage of the BAK is 3.6, but for Samsung it is 3.60. So these two are the major electrochemical differences between two chemistries. Here is the EIS testing procedure. An electrochemical workstation is employed for that, made by the core test, and 50 logarithmically kilohertz to 10 millihertz in this particular range. So in a slightly different note, I would like to mention that this test is a slightly different from a certain different like potentiostatic, galvanostatic or other tests, because here the voltage is the input and the current is the output. Yes, it is. The voltage is the input and the current is the output. Signals the impedance is actually getting calculated. Here we can see the plots of the real and imaginary part of the impedance, as well as the Nyquist, as well as the Bode plot. So the Bode plot is obviously not our use for extracting or modeling the cell, but the Nyquist plot is. So here is the first RC model we have proposed here. And it is the second RC model. It is the third RC model, and it is the fourth RC model. So here we can see that a certain thing, that is L. L is the inductance of the cell. So here we can see that there is a certain negative part of the Z. So that is actually the positive part of the Z. So that is actually representing the impedance, the inductance. So that's why we have modeled in that in such manner. So there next the chi-square minimization by the meta-heuristic algorithms. So here we have from the data part, we have extracted that the Z real and Z imaginary, and from the model we have calculated this Z real and Z imaginary in terms of R, L and C parameters. Now we have calculated the error between the real measured and the real calculated, that is ER, and obviously the imaginary measured minus the imaginary calculated, that is EI. So from there we have developed this chi-square equation, and the chi-square equation is actually our objective function to minimize this with the help of different optimization techniques. So here are some basic equations of the particle swarm optimization that we all know. I think these basics we all know of this kind of meta-heuristic technique, so I am not getting much time on that. And this is also the Gray-Wolf optimization technique, and it is the teaching learning based optimization techniques. So these are some of the most important parameters for any kind of optimization techniques. So these are very much important to run these algorithms. So this is the test results for BAK as well as for Samsung cell. We can see that the measured value as well as the model fitted with PSO, GWO and TLBO. The upper row is actually for BAK and the lower row is for Samsung. This is the convergence curves, that is the most important thing, how the methods are getting converged with number of iterations. We have taken the 1000 as the iteration number irrespective of the model or cell or number of or the algorithm, the techniques. So here is the comparison of error. We can see that here we have been compared here with the RMSE, MAP as well as it is a fitting problem. So for the correlation coefficient also. So we can analyze the result that the model 4 with the optimal parameter obtained from the TLBO is deemed to be the best fit for BAK cell with the RMSE value of 0.0872%, MAP value of 0.0718% and the correlation coefficient of 0.99374. So, but for the Samsung cell, quite differently, model 2 is actually the best fitting one with the help of GWO parameters, and these are the RMSE values, that 0.0915 and 0.06789%, and also the RMA correlation coefficient is 0.09784. So here our approach is to model this with the help of RLC parameter based on its electrochemical impedance spectroscopy results, and we have tried to model this, and the optimal value of these RLC parameters are listed in table 5 to 8. Here are the optimal value of the parameters, optimal value, or you can see that the decision variables. So decision variables are these values. So they have achieved these values for the best fitting conditions. Now we will be moving towards the electrochemical impedance, electrical equivalent circuit model based modeling. So here is the first order equation. This kind of equation is actually for representing the cell for its dynamic characteristics. Like we can see that it is not a direct what we say like this voltage current relationship is linear. It is not. It is not V equal to IR kind of a thing. So here for a non-linear change or the dynamic change, there is a certain linearity is there which can be represented that these I are 0. But there is a certain dynamic part is also there which has to be represented by this VC1. That is the dynamic change of voltage. So here the number of RC branches can be increased. Here we have done our research up to 3 RC level, but theoretically if we proceed to the infinite number of RC branches, the best the cell can be modeled. But for a practical scenario and obviously from the implementation point of view, the higher the number of parameters, the higher the complexity or the mathematical burden to be taken care of the cell is. So that's why people used to go for mostly 2RC model that is best for the for catering both the problems. So here we can see this the equation of the first order model that we have developed, and it is the second order RC model, and it is the third order RC model. So this is a very congested way I can understand, but to represent the whole thing in a certain slide, it is actually can't avoidable. So this is the lithium ion cell specification that we have tested. It is the BAK cell which we have tested for our purpose of modeling the cell properly. So different tests we have performed. One is charge discharge test. One is low current OCB test. I think we have already discussed this for SOC OCB relationship. And the pulse discharge test, which is specifically used for extracting these RC parameters of the cell, and also the drive cycle test. We have, as we have previously mentioned, we have used 3 different driving patterns, and we have tested the cells on how they will work for those particular drive cycles. And all the above mentioned tests are performed for 15, 25 and 45 degrees centigrade. The newer BTS 400 is the testing setup we have used with a voltage range of 0.5 volt and the current range from uh, 0 to 6 ampere. And there are actually 8 channels, and the temperature chamber of ACMS we have used with a temperature range of minus 10 to plus 90 degrees centigrade, but we have tested it for those specifically 3 temperatures. And the BTS client is actually the host computer to be installed for the extracting the signals, that is the voltage, current and charge kind of a thing from the testing setup. And for the sampling frequency we have taken as 1 Hz. Now the test for parameter identification, we have used this voltage current relationship for testing the cell. So obviously the input is current. We have represented here that the current is that should be charged the cell from 0% to 100%, then rest for a certain amount of time. The CCCB charging is the most commonly used one for any kind of a charger or this charging application. So in CC mode, almost 70 to 80% charge is stored in a cell, and the remaining is for the CV mode. And once we have charged the cell, we have discharged it with a certain pulses of 2% drop of SOC and then rest for 2 hours, and we have done this for 20 times. Then next we have changed it from 5% drop for SOC, and we have done for 12 times, and obviously next the 2% for 10 times. So obviously theoretically the SOC should reach 0%, and if not, then we will start with step 2 also. This is the algorithm for parameter identification. Here we can see that the actual voltage current relationship as well as the RINT model that we used in a very first part of our vehicle modeling, where we use the RINT model, and obviously 1RC, 2RC, 3RC model is also there. So here we have used the Levenberg-Marquardt algorithm for solving this nonlinear least square problem. It is also kind of a model fitting problem, but here we have used this LM method, which is highly used in solving these real life problems, and it actually has the advantage of both Gauss-Newton and gradient descent method. So both the advantages of these two algorithms are actually combined in this particular LM method. So these are actually the parameter variation of the first order model with different temperature, and we have made a separate lookup table for that also. This is the variation of second order model parameters, and it is the variation of the third order model parameters. State of charge estimation based on these models. That's why these models are highly required for the model based state of charge estimation. And as of now, the most researchers are using this kind of model based estimation apart from this machine learning based. There are multiple advantage, disadvantage of both the methods. So we will go through one after another. Now here the first equation we can see, that is actually the Coulomb counting equation. Here that is eta is actually the Coulombic efficiency, which is actually taken into consideration with previously the charge discharge test I have mentioned. With that test we have calculated this, and we can see that Coulombic efficiency value at temperature 15 degrees is pretty low. So that's why the most of the researchers, or in most of the research papers, it is taken as 1, but it should not be, because Coulombic efficiency has a great impact on battery performance. So here we have calculated this SOC by the Coulomb counting method. Now there are different SOC estimation methods. Here we have mentioned one is this Coulomb counting one, another one is from the relationship of SOC OCB, but that is not a good option, because for a real life application the cell is never rested for a longer amount of time. So calculating the OCV and SOC from OCV is a really a tough job. And obviously the model based estimations are very well known and well implemented, and there are also data driven approaches are there, which is this feed forward neural network and other deep learning method. So what steps we have used for that online SOC estimation? That is, we have to make a predefined table between SOC and OCB relationship, which is very much important. Then the next factor is the which RC branch or which RC model we are going to select. It might be 1RC, 2RC, 3RC, anything. But for our further research, we have used 2RC model because of the advantages that I have previously mentioned. And for after the model selection, we go for parameter identification of all the mm, parameters of the model. The parameters are identified and validated with the given dataset, and here we have used extended and dual extended Kalman filter for estimating the SOC. Here are actually the extended and dual extended Kalman filter. The steps involved in this Kalman filter is actually the state, output, and covariance. The state in our case is the SOC. The output is actually the voltage, or specifically the terminal voltage, and input is basically the current. And the covariance values are obviously very much important, and there are some initialization of these covariance values, and also there might be noise in measurement, that is known as the measurement noise, that is here VK, and also the process noise. Process noise is actually the W. So these two are very much important, and their covariances are actually Q and R. So we have to give a certain value or certain assumption on that depending upon the data set. So how much error can be there, based on that the covariances values are actually calculated, and these are actually some of the tuning parameters. So that might not be same from dataset to dataset, so somehow we have to tune them appropriately. And from the dual extended Kalman filter, there are actually two states. There are two states, one is SOC and another one is actually bias. And there are also two output and there are two covariances. The same process as EKF, but here the important thing is there are two states are getting mentioned, getting estimated simultaneously. In normal EKF, there is a uh, one state is getting estimated, but in case of dual extended, that is the DEKF, there are two states are getting estimated, and there are other parts consecutively same as the EKF. And the covariance values here, the for table 14 can represent these covariance values which we have used for our purpose. Now the state space equation of the 2RC model we have used here, and it is the state space equation for the DEKF. We have considered voltage bias as well as current bias separately. So for both of them, that the bias value is getting subtracted from the measured value, and the actual value we have tried to estimate. So the workflow of EKF and DKF, with EKF we are estimating only the SOC, but with the help of DKF we are estimating SOC as well as the bias. So in case of bias, we have used voltage bias separately and current bias separately. So this is the basic proposed workflow diagram of our work. First, the model is getting predicted, then the state error covariance prediction is done, and based on that, the Kalman gain is getting calculated. This Kalman gain is actually updating the states and updating the covariance error also, and this covariance error, obviously, in the next iteration, the SOC OCV, as per the new state, the SOC OCV lookup table will get updated, and also the parameter values also. And this updated RC parameter and OCV values are actually giving us the model output voltage, and that will getting compared with the actual output voltage, which is the terminal voltage. Now this is the test result. We can see that real SOC we have taken from the from the testing setup, and this EKF is the one we have mentioned, and DEKF IB is like accepting, like taking care of the current bias, and DEKF VB is considering the voltage bias. So three different temperature we have done here. It is for 15 degree, for three different drive cycle it is for 25 degree, and it is at 45 degree. Now the MAP of SOC and terminal voltage is actually calculated. Here we can see that for the DKF VB at 15 degrees centigrade is actually working best. Similarly, at 25 and 45 also for terminal voltage as well as for SOC estimation, the DKVB is performing better. In the previous case that we have mentioned, their bias value initially we have set as 0. We have assumed that there is no bias. So this is the time difference calculation. Time difference is a very important indicator. The time difference means that when the actual SOC is reaching a certain SOC level, that is suppose 0.1% or 0.2%, the lower region is much important because it is indicating the driver to recharge the cell. So we have taken from 50% to 10% in this particular region, different levels we have set, and we have seen that when the exact time where the actual SOC is crossing these values minus the actual minus our estimated model or our estimate or our algorithm when it is crossing those values. So that is actually taken as the time difference, and here we can say that most of the cases the early estimation is happening. The early estimation in any day is better than the late estimation for this kind of user based application, so that the user or the driver can get a sufficient amount of time to arrange the recharging procedure. So that's why we have seen that this DKVB for most of the cases is early estimating. Here is the effect of the bias. Here is the effect of the bias. It means that if we have considered a certain bias values, That is, suppose current bias is 10 milliampere and voltage bias is 10 milliampere, and they both are actually uh, contributing at the same time, then how the algorithm will work. So if we here from the table we can see that if the current bias is there, we have used the algorithm that DEKF IB. It is actually working pretty well, and obviously with the voltage bias, if we used EKF and DKF VB, we can see that the DKF VB is actually uh, working better. And if both are there, like IB as well as VB, then we can see that DKF IB is actually working best. So if we consider that there is no bias, like if we assume that, then DKF VB is actually working, actually getting better result. But if we consider there is a certain amount of bias, then this DKF IB is working best. So these are the some of the discussions we have done. That initially we have made different models, but based on that we have used the second order one, and lab test experiment allows for precise change of model parameter with SOC. That lookup table we have done for all the parameters with SOC at different temperature. With high fitting accuracy, the average SOC OCP relationship is determined.
Hmm.
We have
Hello. Excuse me, T Bhogras, kindly mute your mic.
Now we have used this extended and dual extended Kalman filter to properly estimate the SOC and the terminal voltage. And because there might be some noise data, so we have considered separately for the bias as well as for the noise, so that both are actually taken care. Now we have moved from the SOC estimation using deep learning method. Here we have used three different deep learning technologies. One is feed-forward neural network, another one is convolution neural network, and another one is long short-term memory, which is a part of recurrent neural network, it's the RNN. So in this case, what we used to do, we just get the signals means that the voltage, current, and temperature from the sensors. So after that, the data has to be properly cleaned. The cleaning of this data is one of the major part, because to get the outlier and to get the actual signal, it is a very complicated thing. So that is properly cleaning the data and standardizing the data. Standardizing the data means to, after cleaning, the data should be properly normalized. Then we should have used different set of, and we have to select the algorithm which one we want to perform, and then we have to train the model, and then we have to validate the model with a certain data set. We have to separate them for training, validation, and testing. So it is a standard procedure for any kind of deep neural network based approach. So to validate the model, we have to tune the different parameters of the algorithm. So there are lots of parameters of the algorithm. So here we have to properly select that depending upon different data set. So once the model is getting validated, the model will be tested. It is a standard procedure. So here is the lithium-ion cell specification. We have taken the Samsung cell and we have performed these drive cycle tests, that NYCC, UDDS, and BCDC for three different temperature. It is the feed-forward neural network. Here the first one is the input layer. So what are the inputs? The inputs are nothing but the voltage, current, temperature, but not the raw data. We have somehow processed them. We will come to that part. And then that hidden layer is actually combining the bias as well as the weights and biases values are there, and finally the output is there, and the entire thing is actually working on the backpropagation method. That first the bias values and the weight values are set, and they will give the output, and this actual output will get estimated with the with the actual this estimated output will get compared with the actual output, and the error will be minimized. And in the same case, the this ADAM optimizer is used, the adaptive minimum optimization that is used here. So this is the certain standard network for FNN. And for the convolution neural network, here actually from input there are different features are getting extracted in the convolution layer 1, and similarly for convolution layer 2, and then the information is getting passed to the fully connected layer, and the output is getting calculated. So these are the steps involved in the convolution neural network, where the matrix is not getting multiplied directly, but they are actually convoluted. So that's why the name is convolution neural network, though it is mostly used for the image recognition kind of a thing or signal processing part. But here we have used this 2D convolution network for our purpose. And it is the long short term memory which is actually taken care of the it actually has the memory, that is the in the previous case we have seen that it is not a function of a previous time step data, but here we can see that it is actually taking like considering the previous time step data, and based on that it is trying to like update itself. So for training the model, there are actually different number of neurons we have used. For FNN is 50, and for the CNN, the convolution layer of 1 cross 2 we have used for the first layer, and similarly for the second layer with the number of neurons are 10 and 15, and the stride is 1, and the number of hidden unit for LSTM we have used is 75. These are some of the optimal values to we have taken after running the data for different algorithm. We have came up with this kind of a optimal value of this model hyperparameters, and the entire data set is actually getting divided in 3 different parts. The major one is taken for training the model, because properly training the model is the most important thing, and then the rest 15% for validation, and the remaining 15% for testing the algorithms. So in figure 62, we can see that the basic structure of this. So the parameter, the performance indicator is MAP and the RMSE. So once we get the best performance, we will stop the algorithm. So we have continuously using these 3 algorithms at a time. And the optimizer we have used here is ADAM with a learning rate of 0.001. The epoch is 2000. The batch size is 1000, and the activation function we have used here, that rectified linear unit ReLU, and the exponential decay rate is 0.9 and 0.999. So this is the testing result. So with the testing result, one thing we would like to mention that we have not directly used the raw data set. What we have done, we have processed the data set as per our need. Our need is estimating the SOC as accurately as possible. So first what we have done, we have properly downsampled the data, because the entire data set is pretty larger. So dividing, though dividing is done for training, but still we have downsampled them. We have properly downsampled them so that it can replicate the original signal. Downsampling is with a proper rate is a very much important thing, so that the outliers can get out, but the actual dimension or actual representation of the signal should be maintained properly. So this downsampled, we have taken a rate of 4. And another thing is sampled mean. The sampled mean, what we have done, we have taken a sample mean value with the same rate of 4. Instead of taking the raw data, we are taking sample of 4 data sets. So in this way, we have made these inputs, that is the current, voltage and temperature. These are the raw inputs that we have given to the models, that these neural network based models. And we can see how it is actually getting a certain different values. But for the output, our output is SOC, so that we have not done anything. We have only downsampled it for matching it with the number of data points or the number of dimension for input output side. But we have not we have not taken any sampled mean or anything. We have just downsampled it, and then while representing the results, we have upsampled it as well. So it is the model testing for final SOC estimation. Here you can see that the first data set, that the first row is for downsampled, and the down row is for sampled. Seven are representing the UDDS drive cycle. This one is NYCC, and this one is the BCDC. Now we have to compare the MAP for downsampled mean and for the downsampled inputs and the sampled mean inputs. Here we can see that for all the cases, almost the sampled mean inputs are actually performing better than the downsampled inputs. So here we can compare the drive cycles, we can compare the temperature, we can compare the algorithm. For any kind of a thing, this second approach is actually giving us better result. Now the discussion. So for two separate scenarios we have created. Based one is with downsampled and another one is with sampled mean. The machine learning based techniques has the advantage of being able to self-learn and update its internal model parameters. And important another phenomena is it also precludes us from simulating the battery and performing manual computation on its characteristics. That is, no such model is required. Like with the previously we have done Kalman filter, for that a model is important, but here no model is important. It will just consider the data as a black box. It will input the data to a black box and it will take the output. The internal chemistry, the manufacturer, the relationship, the temperature is also not a directly implemented parameter. We can see results at different temperature, obviously, but it is taking all the signals as a data set. So for that, it is not considering the exact electrochemical or electrical parameters that we consider. For it, it is the input to the black box data set. So at 15 degrees centigrade, the with FNN and UDD, with FNN, UDDS shows much higher SOC MAP with 6.5978%, whereas in case of NYCC and BCDC, the values are 2.7098 and 2.374. Similarly, MAP values are observed for UDDS and NYCC at 25 degrees centigrade were trained by FNN, which are 3.8851% and 3.8161%. But for BCDC, this value is quite lower, around 2.5561%. At 45 degree, highest MAP is achieved for UDDS, which is 2.3289% with respect to NYCC, and BCDC, which is 0.7781% and 0.9586% when trained by FNN. So if we compare the temperature, the best is actually we are getting as 45 degrees centigrade. Now we will come into the state of health estimation. So what is state of health? We all uses our mobile phones, and we have experienced this previously, that when a phone is new, it is actually lasting longer, maybe suppose 1 day or 1.5 days. But as after 2 years, we can see that it drops its charge very fast. So that though we are seeing 100% as the battery charge, so but the point is the amount of charge retentivity, or the charge that can be retained by the cell, is actually getting lowered with its usage. So initially the capacity is a CAP, suppose P is the present state, its capacity, and this cap norm is the nominal capacity or the capacity at its BOL. The BOL is actually the beginning of life. That is when the cell will start working. So this ratio is actually called the state of health. So it is to be represented in percentage also. So the capacity estimation for a certain cycle is one of the most important thing, because it is not a linear kind of a relation it used to maintain with a cycle. So when we are telling a cycle, the cycle means a full charge and a full discharge is actually making a one complete cycle. So for estimating the state of health, we have taken the NASA prognostic domain. So this data set consists three different charging profile. One is charging, discharging, and impedance at the room temperature. Here we have considered only 4 commercially available 18650 lithium-ion cells, which are numbered as 5, 6, 7, and 18. So in the entire analysis, they have tested the cell in the same environment with the usual CCCP mode, and the discharge is also with a constant current. So here in table 23 we can see that is battery 5, 6, 7 and 80. This charging is constant, that is from 1.5 ampere. The upper cutoff voltage is 4.2 and the CC mode ends and CV mode starts when this cutoff current will come down to 20 milliampere. And for the discharging it use 2 ampere, and for the cutoff is that the lower cutoff voltage is 2.7. So all the cells are getting tested at room temperature. The initial SOC is actually not 100% for all the cells, so it is like 92.82% for the first battery, and it drops up to 66%, and similarly for others also. So how we have selected the feature? So for continuing this research, our approach is to find some of the directly measurable or capturable parameters. Those can be directly measured by a layman. So that's why we have taken the delta VDC. Delta VDC is actually the temperature difference for every cycle while discharging. And this voltage difference is nothing but the voltage at the first instant and the voltage at the last instant of a particular cycle. So this VT1 minus VT end. Similarly, the temperature and the time. So you can see all these three parameters, they can be measured with a voltmeter, with a temperature sensor, and with a stopwatch. These three parameters can be estimated, can be captured. So we have tried to make a certain model which can directly give, which can directly take these inputs, like these three inputs, and produce the output, that is the SOH, accurately. So here is the raw data we can see, that is the delta VDC, delta temperature DC, and time DC, and the SOH also for all the cells. And here, as per the data sheet, it was mentioned that the 70% is basically the threshold limit. So once the cell is reaching 70%, that means it is actually reaching its end of life. The end of life doesn't mean the cell will not perform anymore. It means that their reliability is not assured after that certain life. It may work well, that is not the issue, but the point is how long or how much reliable their work beyond this, like lower the 70%, that is questionable. So here we have made a correlation matrix with the target. Target is the SOH, and the inputs or the features. Here is our proposed framework. We have the initial state as t equal to 0 and final state as t equal to end, and we capture all these parameters, and we have done this min max normalization. Then we have trained the model. We know, we have already seen that there are around 160 to 170 cycles for each of the cell. So, but for a machine learning perspective, there is a larger data set required. So that's why what we have done for the training validation purpose, we have clubbed 3 cells data and we have tested the next cell. So in this way, we have done for all the cells, we have clubbed 3 cell and we have tested the 4 cell. So this training validation part is also very important for us, because training validation we have made separate ratios. We have split them in 5 different ratios, like from 10%, 90% to up to 50%, 50%. In this ratio, we have divided the entire data set for training and validation purpose. Next, we have put them for training the model. There are two models we have considered here. One is FNN and one is LSTM. And with this training section or the training portion of the entire data set, we have trained the model. With the validation section, we have validated the model, and we have tested the model with the fourth set. With the fourth cell of the testing data set. So here we got the optimal structure. Optimal structure means how should be the training validation ratio and what are the other important parameters that we have to fix here. That is the in FNN also number of neurons, and in LSTM it is the number of hidden units. We also have varied them so to find the optimal structure. And now the SOH is getting predicted and the performance with the actual result is evaluated and the end of life is estimated. So here is the model specification. Here we have considered two different scenario. One is with 2 inputs and another one is with 3 inputs. So with 2 scenarios, we have 2 inputs means with only voltage and time, and 3 input means voltage, temperature and time as well. So we have considered in this figure, we have considered the average correlation coefficient of inputs with the output. And the various structure of FNN and LSTMs are used with different training and validation ratio. And we have seen that for training the model, FNN is taking only 15 seconds, but LSTM is taking around 2 minutes of time. So the number of hidden layers in FNN is 1. Now number of neuron in one fully connected LSTM is 10. Loss function we have considered is mean squared error. Optimizer same as the previous ADAM. Learning rate is 0.001. Epoch is 500 and batch size is 50. And active function, that is the ReLU we have used here. And the training validation ratio that we were talking previously, it was actually varied from 90%, 10% to 50%, 50%. And the number of neuron in FNN we varied from 3 to 7 to get the optimal value. And for the hidden unit, we have varied from 3 to 7. That the number of hidden unit for LSTM. So here we can see that the error is the value, that the validation error between the, and obviously it's table with number of neurons and number of training and the ratio of training testing data set. So for both LSTM, FNN, for both 2 inputs and 3 input scenario. So with optimal function, we can see that the ratio that with optimal FNN1, the ratio is best as 9:1, that is 90%, 10%. The number of neuron is 3 and MAP is given as 2.29% for 2 inputs and 1.86% for 3 inputs. And similarly, that for the optimal LSTM structure can be fetched here is when the ratio is 7:3, the number of hidden units is 3, and the MAP for 2.41% for 2 inputs and 2.21% for 3 inputs. So if we compare all of them, we can see that 1.86% with 3 inputs with this optimal structure of FNN is actually producing the best result. So here is the model testing result. Here we can see one important thing about cell 7, that is it is actually not crossing the certain threshold level. So we can see it has not reached its end of life yet, but the other cells has done. Now it is the measure of model accuracy. So model accuracy is getting calculated with RMSE, MAE and MAP. So all the 3 parameters are calculated from cell 5, 6, 7 and 18. Now error analysis. The error analysis is very much important from the hyperparameter part. So the number of hyperparameters, the number of mathematical burden it used to take. But in case of real life application, that is BMS, so it should not be a certain high value of hyperparameter that can that can estimate the model, but it will take a certain number of time, and the amount of memory required will be also high. So our approach is to find a certain structure that we have received for the FNN with 3 input scenario, where the total number of hyperparameter is only 16, and it is also giving us the best result in terms of error comparison. Now end of life calculation. So end of life calculation, we can see that is as the 70% is made the threshold. So like it is also same for the SOC thing. So this early estimation is obviously better than the late estimation. So these negative values are actually indicating the early estimation. So we can see that in this particular figure 79, that for 2 input case and for 3 input case, figure 5 is actually giving us early indication in 3 input, while in case of cell 6 we can see both the methods, that FNN and LSTM, they are actually giving us early inputs, early estimation. But for cell 7, as we previously mentioned, that it is not even reaching its end of life, but battery 18, it is both the cells are actual, both the scenarios and both the algorithms are giving late estimation with a value of 5 cycles. So this discussion, we can see that the best features are extracted based on its initial and the final state, and the parameters can be easily extracted. The parameters are highly correlatable with SOH, and these two ML-based algorithms we have used, we have taken separate architecture from them. We have tried to come up with the optimal one, and then for both the models we find the average NAP, and the end of life is also getting estimated properly with the help of 3 input FNN model, and the best algorithm, which is 3 input FNN with 10%, 90% training and 10% validation data set with 3 neuron is giving the NAP of 1.86%. Now for another part, for the state of health estimation, as we have previously seen, we have taken inputs from the discharge cycle. Here we have taken a slightly different part. We have taken the features from the charging cycle. So from the charging cycle, we are trying to estimate how the SOH can be predicted easily. So for that we have used this Oxford battery dataset, where 8 cells, these are pouch cell, so their data was provided, and it is also in public domain for user. So here we can see in the fresh cell how the voltage is actually changing. Similarly, the capacity is changing and the temperature is changing from the aged cell. Aged means at the last cycle of that particular cell. So here we have, for the representation, we have cell 1 data. Now similarly, the data processing and feature extraction. The raw data we have taken are voltage, charge and temperature. We have properly smoothed them with the Gaussian function with a smoothing window of 100. Then we have downsampled it so that it can properly replicate the entire data set without losing any kind of an information. So these process data are used for the feature extraction. Now we have made the incremental capacity analysis, which is actually directly giving the health, aging, or the aging condition of the cell. Here we can see that in the fresh condition, that for the first cycle, there is a certain there are actually 2 peaks which are highly meaningful. The first peak is actually the anode peak, and the second peak is actually the cathode peak. So, but as the cell is aging, we can see that for the last cycle, the first peak is actually demolished and the second peak is obviously shifted right, and this intensity is obviously getting reduced. So the second peak is one of the most important electrochemical parameter for the cell. So it is not only based on data, it is also an electrochemical process that we need to take care of. So that intensity is the dropping of intensity is actually implicating the LLI. LLI is the one of the electrochemical degradation parameter, that is loss of lithium inventory. This peak is actually meaning that how when it is decreasing, that means the LLI is happening. And once this peak is shifting towards higher voltage, that is shifting right, that means that loss of active material, that is LAM, is coming up in the picture. So both of these part is very much important for us for proceeding our work. So here there are the most important features intensity of second peak, the charge capacity between 3.8 to 3.9, the variance of the charging voltage, and the skewness of the charging temperature. So all these features we have extracted, and our target is SOH that we have to estimate. So here we have taken cell 1, 3, 5 and 7, as there are 8 cells. We have taken odd cells for training the model, and we have used the trained model individually for the 4 other cells for evaluating its performance. Here are the regression algorithm we have used. Here the linear is actually not a certain linear, but it is actually a logistic regression. And then the decision tree regression we have used, and random forest and support vector regression. These are all similar kind of regression approaches we have taken care. These are very simple to implement in case of a BMS, and even online implementation or application can be done with these regression methods, as they does not possess a certain higher amount of memory usage or certain hyperparameter which was involved in case of machine learning. These regression models can be very simply, they can be used. So training and testing of algorithm. For training the data set, we have combined cell 1, 3, 5 and 7's data. And for testing the cell, we have individually tested cell 2, 4, 6 and 8. So with the logistic regression, this decision tree, random forest and SVR, we can see that how this MAP of SOH is actually calculated. Here we can see that for the logistic regression, the all the values are almost minimum with respect to the other algorithms. So the discussion we can come up with, the features are extracted from the charging cycles only, no discharge cycle feature was getting extracted, and all the features are highly correlatable. Once we are taking highly correlatable, it means it is obviously greater than 0.8 and less than minus 0.8. So positive one is like positively correlated and negative one is negatively correlated. The higher the correlation is, the better to like correlate them with the actual values. So the odd number of cells data are combined to create a larger data set, because here is also the same issue with the amount of data. And individually even cells are tested to check the model accuracy. Among all the algorithm, linear or logistic regression is simplest to execute, and from the performance basis also it is outperforms the others. And for all the 4 cells, the maximum MAP is even less than 0.5%. So here are the conclusion and future scope of our entire research. So the vehicle model is developed considering all the possible forces with the help of simulative battery pack. The vehicle electrical models, that is EIS based and ECM based, are developed to represent the internal behavior of the cell accurately with the lab tested data. For accurate SOC estimation, algorithm derived from the Kalman filter is used considering the real life EV scenario at different temperature. Then we have taken deep neural network based techniques for SOC estimation considering raw as well as processed data, input data, and compared To study the degradation mechanism, the proper health estimation, feature-based machine learning approach is provided. With deep neural networks, simple feature extractions from discharge cycles are used to estimate the state of health. With regression approach, we have taken charge cycle-based features and used for SOH estimation. In future scope, all the models and algorithms will be implemented in BMS for its online application. We would like to acknowledge Professor Shatilekha Ghosh of Dr. M.N. Dostu School of Material Science of Engineering of IIST Shivpur and Nunam Technology India Private Limited, a Bangalore-based startup, for testing all our cells under their lab setup. Here are some of the references that we have used in this presentation. Thank you. Thanks to all. So now I would like to take some questions or feedback from your end.
Sir, am I audible?
Yes, yes.
Sir, I would like to ask that you have used different models for different conditions to test or to inquire about the different conditions of the battery. So, is it possible that with same approach or same models we can do or process each and everything or test each and everything related to battery?
I didn't get your point exactly. Like I have tested for different life cycles and for different temperature. So this kind of.
In one case
Sorry?
you have used a regressive model. In another case you have used different.
Yes.
So
Just to compare.
Achha. Otherwise
just to compare that how to implement them, because like as per my knowledge, in BMS there is a very certain small pace is there apart from implementing this algorithm. So for that, in as per now in India, all the like large automotive section, they are using the simplest one for SOC estimation, that is Coulomb counting. And for SOH estimation, you can get astonished, but no one is implementing any kind of SOH algorithm presently in present scenario of India. Okay, so because no.
AI is yet to be implemented.
Yet, like even the Kalman filter based or regression based approach that I have presented here, nothing is presently using in any automotive sector of India. They are only estimating this SOC based on the simplest or the what is the erroneous Coulomb counting method. There are different drawbacks of Coulomb counting. I think you guys have already have some idea about that. But for SOC estimation, it is getting used. But SOH estimation, the everything they are using, considering the cell health is 100% or 99%. So that is one of the, because the BMS that should be developed by their own, because most of the BMSs currently using are from imported from China. So like developing their own cells, developing their own BMS is a very important, like very challenging. Obviously, it takes a lot of time, effort, good resources, and all. So that is one of the major issue, because you guys have all seen that there are some blasts of scooter is already there. So that is one of the major thing, because BMS should be made in house, because one BMS that is using in suppose Russia, where the temperature is below 10 minus 10 degree, and we are using it in suppose Punjab or Haryana, where temperature is around 45 to 50 degree. So the same thing will not work.
Okay, so temperature conditions should be met according
temperature condition is the most important thing in case of BMS application.
Okay. Okay, sir. Thank you.
Hello, sir. There is a question in the chat box.
Yes, yes. Sorry,
Yeah.
okay. Just a second.
Uh,
Yeah, so
no.
sir, while using in EV application alone, we have to concentrate on battery temperature, or it should be seen for all energy storage application. Look, actually, all energy storage application, they are almost static one. But in case of EV, the entire thing is actually dynamic. Like in a road, the vehicle is running, so this road temperature is important, and and within the vehicle, the battery pack is placed in a certain place. So with the other so other mechanical components are also there. So everything is actually getting heated up, and if there is no properly cooling or coolant is used, so temperature of the this battery pack will obviously get increased. But in case of other energy storage application, it is mostly in household condition. So here there is a certain temperature, and it is also not a dynamic position it is taking. It is within a certain static condition. So their temperature is not much affecting because it is not much getting used.
Any questions from participants? Uh, I think there are no more questions from the participant side, sir. Thank you very much for
Okay,
delivering.
okay.
Thank you very much for delivering such a wonderful lecture, sir. I think our participants will utilize for the maximum benefits. Thank you very much once again for a wonderful lecture.
Okay. Thank you. Thanks a lot. Thanks all of you.
Thank you, sir.
It's a very nice presentation and lots of information. I hope participants are also getting benefited with your nice presentations. Thank you for giving your valuable time to us.
Thank you, sir. Thank you. It's my honor.
Okay, bye.
Okay. Bye.
Participants will meet next session by 5:45.